Let's continue on with this control volume method. We finished up the sketch and observations last time, and so now we're going to just take a look at this one volume element and perform a mass balance. Okay, so we're going to come up with what's called the continuity equation, and this is a conservation of some property. In this particular case, in this section, it's going to be the conservation of mass. Right? So that basically just says that we need to take into account all the mass in our system. So if I know how much mass is entering and leaving this particular box, then that better tell me how much is left in the box, right? If these are different. So I can't have mass just disappearing or just showing up. Okay. So that's our continuity equation. So we're going to look at the conservation of mass. Later we'll look at energy for the thermal case, and we'll look at momentum for the fluid case. So the continuity equation just says that the rate of the accumulation of mass, okay, how fast mass accumulates inside of this, and that could be a negative, so it could deplete. Right? That'll just depend on how the problem works out. But the rate at which the mass basically changes in here is going to depend on the rate at which the mass comes in, that's our flux, minus the rate at which the mass exits. Right? Hopefully that makes sense. If we have a lot coming in and little leaving, then we expect to see an increase in the mass inside of this box, right? Or vice versa. If we have a lot leaving based on what's coming in, then the concentration in this box will go down. Okay, so how much that mass changes in this given volume is just how much is entering minus how much is exiting. And so we can go ahead and start putting that in mathematical terms. So the rate that of accumulation of mass is going to equal the volume of our element times the change in the concentration with time. Okay, let's see if that makes some sense. The concentration is a mass per volume, right? Grams per centimeter cubed. So that's why this volume is out here, right? So the volume then terms would cancel, and then we'd be left to simply grams per second. So that's our rate of accumulation of mass, grams per second. All right. And then this is going to equal our flux in the x direction, because we only have a one-dimensional problem. That flux, remember, is a grams per area per time. So we need to multiply that by the area that it's coming in. So the areas would cancel, and I'll have simply grams per time, right? Grams per second, which is, again, the same units we just talked about over there. And so this flux times area is evaluated at position x for our volume element. Okay. So this allows for the possibility that the area might change at different positions as well. That's why the terms are together and they're both being evaluated at x. In this case, for the rectangular system, the A is independent of x, and so we could pull this out of this evaluation. Okay, but that's not going to be true for the cylindrical case. And hopefully you've guessed that the rate at which the mass exits, same term again, but we're going to evaluate now at the exit surface, x plus delta x. Okay, so that's this area right here. All right, so the area is constant in our problem because we have a rectangular system. These two areas are identical. And so what we can do is we can go ahead and pull the area out of these terms. So I'm going to have the area sitting out front here. Okay, the volume here is the area times delta x, the thickness, right? One surface times delta x. And so the area that I then have for this term and the area I pull out from here are going to cancel. And what I'll be left with over here then is just the delta x piece. And then I'm going to divide by delta x to bring it over to this side. So there's where this came from. Okay. So we've got, again, the flux at position x now, minus the flux at x plus delta x, and that's all over delta x. So just rearranging this, substituting v in. Okay. The other way I guess you could think about it, you're just going to take this, substitute it in, divide through by the whole area, the whole volume. So this would be a delta x, and then that a that was here will cancel out of both of those terms. All right, so there's my equation. Now, if you recall in calculus class, I guess maybe even pre-calc class, the definition of a derivative, the definition of a partial derivative, okay, df dx, is the function evaluated at a position x plus delta x minus the function evaluated at a position x. Right? So we just take the difference in the value of a function at some point and some point very close to it. And that's basically what this is saying. So f plus at x delta x, f at x. And we divide that by that difference delta x. And then we take the limit as this goes to 0. So basically these two values get closer and closer together. So this gives us a change in the function value, right, versus a distance. And that's our derivative, df dx. Well, that looks like what we have here. If we now, in the limit, let delta x go towards 0, so our volume element becomes very small. That's what we want to do. We basically have the definition here of the derivative function, the partial derivative function. The only difference is that our two terms are switched based on this. And so we'll have to throw a negative sign out here, and then we can flip these two terms. So we have the definition of a negative partial derivative. Okay, so dc dt then is equal to the partial derivative of the flux with respect to position. And there's the negative sign, again, to switch these two terms. So dc dt is equal to the negative of the flux with position. And this is referred to as the continuity equation. And this makes sure that we don't violate mass conservation. It's taking into account all of the mass. So the concentration that changes, the concentration change per time in a given location in our material is equal to the difference in the fluxes around that location. Okay, hopefully that makes sense. If our flux is constant everywhere in our solid, then the change in flux with position is 0, and then therefore dc dt is 0, and what that means is that our concentration is not changing at all in our solid. So we can have concentration differences in the solid, but they're not changing anymore. That's actually steady state. All right, so there's our continuity equation. So we're going to use that next time, and we're going to take the constitutive equation. So we'll recall what that is, and we're going to put it into this one and continue on in this problem.